Hey, this is Dave with OC Astronomy. I'm here again with presenting the Openstax textbook material available at openstax.org, and they have a free textbook for astronomy. And this is the classroom material that I hope will give my students a condensed version of the chapter material lectures so that you can do better on your quizzes. And if you're enjoying this but you're not a student of mine, then feel free to enjoy the video. I'll try to keep it short. And we're going to go through chapter 4 today, chapter 4 of Openstax Astronomy textbook. We're going to look at the Earth and the sky and how they move. We're going to look at the seasons, how you keep time, the calendar and the calendar reforms that have been necessary, the phases of the moon, the tides, the oceans, and the eclipses, all the things that have to do with how the Earth and sun and moon move. Thanks to good old Copernicus defeating Ptolemy in the realm of ideas, we have a new idea that the Earth moves around the sun. And as simple as it seems to us now, that wasn't always the case. And convincing the people of Earth that the Earth indeed was moving was a little bit difficult. And it took a little while, but then shortly after Copernicus's ideas were accepted as right and Kepler came along, refined the motions of the planets from being circles to being ellipses, that helped make the math work a little better and be more accurate. And that allowed people to accept the model a lot better. Soon after that, though, it just became the accepted model, especially after Isaac Newton came along with gravity, his theory of how gravity works. And from then on, it's been pretty much accepted that gravity causes the Earth to move around the sun. It also causes the moon to move around the Earth. It keeps us all on planet Earth, thankfully, and all with all the creatures and air and water that's on our planet. But there have been some refinements since then of how exactly the Earth moves. And as far back as the Greeks understood that the Earth seem to wobble a little bit through space, and that the fixed stars, although they look fixed from night to night, over the course of many thousands of years, they will make a complete circle around of one wobble, and you'll get the stars will appear to move from their exact locations. They're not even pinned down. And there was a French astronomer named Camille Flammarion. It's funny, I've only read that name, I've never pronounced it, so I'm probably pronouncing it wrong. I've only said it in my head because who uses the name Camille Flammarion? I assume that's how you pronounce it. But he was a Frenchman, and he was a popularizer of astronomy, and he wrote a wonderful, wonderful textbook in the 1800s. And in his first couple of chapters, he details that there's at least 10 motions of the Earth that we know about now. You have the wobble that I just briefly discussed. You have the motion of the Earth around the sun. You have the Earth's own rotation. You have the moon going around the Earth, which causes it to be pulled one way or the other. You have the fact that the sun is not exactly rotating on its center of gravity, so it's slightly off of its center of gravity, which causes our center of gravity to shift along with it as the other planets tug on the sun. And then the whole shebang, the sun and all the planets are moving through space along with the Milky Way as we rotate around the center of the Milky Way. And so the Earth is actually spiraling through space. But that's just enough to blow your head and make you crazy. So let's just focus on the motions of the Earth as it appears to us. So the first thing to look at, I have a handy model of Earth here. We see that the Earth is round. Big news flash, not flat, round. So the Earth is round, or actually it's an oblate spheroid, if you want to be technically right. It has a bigger bulge in the middle. It's a little bit flatter on top, but for all intents and purposes, it's a cue ball. It's round. And so if you want to define your position anywhere on a round sphere, you need some coordinates. There's something called a great circle, and a great circle is any line that goes around a sphere that is centered at its origin or the center. So the equator would be an example of a great circle, and then also these lines that go north and south We call them longitude lines, but any line of longitude is a great circle centered around the center. And we call those meridians. So you have, you can name any meridian. There's a couple of them that are famous though. One of the most famous is outlined with this black and dotted line here, is the Greenwich meridian. And so you have a line that goes through Greenwich, England. Hey, plug my own video on the subject. If you look on my channel, there is a video of me at Greenwich, England. So you can see the observatory that's there, and you can see the line that goes there. Now, since the Earth is round and it rotates in this direction, the line that goes through Greenwich is just arbitrary. And the reason it goes through Greenwich is that they built an observatory there, and they had telescopes, and they pointed those telescopes straight up. And what they noticed is, as the Earth rotates, as the Earth does its rotation, then the stars that are directly overhead appear to move. And so it actually rotates, I guess, this way. So as the Earth rotates this way, if you're on a point here in Mexico and you're rotating this way, then you're going to have some stars that are directly above you, and then a little bit later on, those stars are going to be behind you this way, and then a little bit later on, those stars will set just like the setting sun. And so all the stars in the sun appear to rotate from east to west. So an interesting thing about latitude is, latitude lines though, the degrees are, as you go up in latitude from the equator or down in latitude from the equator, as you go 1 degree closer to the pole and you go another degree closer to the pole, each one of those degrees is equally spaced because you're moving along a longitude great circle line and you're centered on the center of the Earth. But if you're moving in longitude at the equator, you have a lot longer space for a degree than if you are up here at the North Pole and you're moving in a degree. If you can imagine Santa doing a little jig around the North Pole, then he's actually not having to go very far to cover all 360 degrees. He can even do it like this if he's standing right on there. I've gone 360 degrees around the world in longitude. But if you wanted to go 360 in latitude degrees, you would have to make the entire trek all the way around. And so that's another difference between longitude lines and latitude lines. All right, so that's a little bit about finding your position on the Earth. Now, what do you do, though, if you're trying to find your position in the sky? Well, you take the same idea of those longitude and latitude lines, but you have your lines here and your lines here, but now you project them out into the night sky, and they become lines here and lines here, but you don't want to call those lines latitude and longitude or else you get confused. So what they do is they call the lines as you go closer to the North Pole and then to the equator, they call that declination. And then the lines that go around the Earth instead of longitude, the lines that go across the sky, they call that right ascension. And there's an interesting reason for that. Go back to Greenwich, if we have our Greenwich, England here. In the video that I have on Greenwich, England, I show some telescopes. The Bradley Transit, the Haley Transit, and there's another transit telescope in there that's located right on the meridian line. And the way that those work is those telescopes can only move north and south. They can't move east and west. They're constrained and they only move north and south. So what do? What you do is you wait for the Earth to move you, and then you can look north and south again, and then you wait for the Earth to move you, and you look north and south again. And so you let the Earth move you through the sky at a constant rate. And what you do is, and what they did is, you declare one day to be day 0. Let's say that it's the spring equinox. And at the spring equinox, you pick a time, let's say midnight, and you name a star that's directly overhead at Greenwich, England, at midnight on the spring, at the first of the spring equinox, or something like that. You can make any arbitrary day, but you call that 0. And then you just wait, and the Earth carries you along, and then the thing that's overhead next, in an hour's time, you mark that star down. And then you wait another hour's time, and you look around and find a bright star, and you mark that star down. And before you know it, you can build a star globe or a star atlas that shows you the stars as they rotate over your head. And maybe you can see that these stars are going to rotate over your head. And at any particular time, if you wait an hour, then you'll have 15 degrees on that sphere. You wait another hour, another 15 degrees, and after 24 hours, you get back to where you started, and that's how you get your hours of right ascension. And the reason why you call it right ascension is that if you are looking north from the Greenwich Transit Telescope, if you look over to your right is going to be the east, and if you wait an hour, you're going to have stars that are 1 hour later in right ascension. Right ascension. It's to the right and it's ascending. And you just watch those stars go overhead, and in 24 hours time, you'll be back to where you started. Of course, during the daytime, or the nighttime, you're only going to get 10 to 12 hours of darkness, maybe, plus or minus a little bit. And so you can only measure those stars, but then over the course of a year, you can build up a star atlas and build up all the stars that are in the sky that way. And so that's how you get your right ascension and your declination coordinates, and you can build a really accurate star atlas. But that also gives you something else that you can notice. While that's been going on, and you're building up your star atlas, and the Earth has been shifting around the sun, you actually notice that if you look at the sun at noon, and you wait until the next day, and the sun comes around at noon again, if you look at the stars that were directly overhead at midnight, so you're looking this way now, you're looking out at the stars, those stars don't come exactly back around to be directly opposite the sun. Because let's say it's noon one day and it's midnight another day, you're looking at the stars at midnight. Well, now the Earth is going to make one step around the sun in its revolution around the sun, and the stars that were here at midnight, now they're going to be here. And then if you wait another day, they're going to be here. And so over the course of a year, the stars will march along the sky by about a degree every night. It's 0.9 of a degree, and because it's 360 degrees that you'll come back around to the same star, and it takes 365 days for that to happen, and so it's about 0.9 some odd degrees per day that the stars appear to shift in the sky. And the difference between that shift and the sun coming to be directly overhead at noon is called a sidereal day. A sidereal day is the day that it takes for the stars to make their revolution to come back to being directly overhead. That's one sidereal day, but then the sun being directly overhead is a solar day. And there's a difference between that of about 4 minutes. And so as you step around and the stars shift over by about a degree, you get about a 4-minute time difference between a solar day and a sidereal day. Another thing is happening as you move around. They've noticed that the Earth is tilted. So you have a tilt to it, and what happens is the sunlight coming in when the Earth, if this is the sun and this is sunlight, the sunlight that's coming in now at this particular stage of where the Earth is, let's say that I'm aiming at Brazil and on the sun. My sun rays are hitting Brazil directly, but my sun rays are hitting New York or Nova Scotia up here. They're hitting it at a glancing angle. And so up here, the sunlight is not direct, it's at a glancing angle, but then at Brazil, it's direct. So down here at Brazil, it's going to be hotter because you have direct sunlight rays hitting it. And you'd call that summer. And then over here, they're going to be indirect. Now, the tilt of the Earth, let's make this the tilt. It's about 23.5 degrees or whatever. So it's aimed at the sun like so. Nothing is going to interfere with the Earth's tilt as it goes around. It's going to stay tilted the same amount. It's just going to wind up on the other side of the sun. And so now you have your sun rays, your Earth is tilted the same way, and you now have sun rays hitting directly on Japan and a glancing angle down here at Papua New Guinea. And so your direct rays are now causing summer in the northern hemisphere. And then when you're back here, when the Earth is halfway through on either side of the sun, those would be your fall and your spring equinoxes. And it's caused because of how the sunlight's rays are hitting the Earth and the Earth's tilt. Got it? So we know that as the Earth comes back around, we can say that the Earth comes back to the same exact star overhead, and we call that 1 year. But it's 365 and a quarter days for that to happen, because the length of time for a solar day and a star day, a sidereal day, are different. And so for the Earth to make it back around to have the same star located over Greenwich, England, at midnight on the first day of the spring equinox, or whenever you want to set it, for that to happen is going to be 1 year, 1 exact years as we call it, but it's 365 solar days and a quarter. And so that quarter of a day really threw things off. It messes with how you tell time, it messes with the calendar, and so forth. Another thing too, I meant to mention, because the sun's directness, and as it goes throughout the changes, the sun appears to be directly overhead down here on something called the Tropic of Capricorn in the south. That happens during the time of year when the sun is in the constellation Capricorn. So back here on the other side of the sun, you have the constellation Capricorn, which you can't see because it's daytime, but that's where the sun is, and the sun is hitting directly as far south as it will go. And then as you go around, you're going to notice that the sun is going to line up then with the equator at a certain point. So there-ish, the sun's going to be lined up with the equator. And then as it goes back around, our sun is going to be located here for the summer in the northern hemisphere, and the sun is going to get as high as the Tropic of Cancer here. And on the other side of the sun, the constellation of Cancer, and that's where the sun is, but you can't see the constellation because it's too bright, because the sun's in the way. But the sun is in the constellation of Cancer. So you have your Tropic of Cancer, your equator, which also happens on the equinoxes. That's when the sun is directly overhead, or appears to be directly overhead there. And then you have your Tropic of Capricorn. And what that the effect that has is, in the wintertime, if you're in the northern hemisphere, you have a shorter day, and if you're in the southern hemisphere, you have a longer day. And then when you get around to the spring and fall equinoxes, that's the word. When you get around to those days, you have about an equal amount of daylight and nighttime at the equator. And then whenever you are in winter in the northern hemisphere, you're going to have a shorter day, and you're in the summer in the northern hemisphere, you're going to have a longer day. And so those are the apparent solar times, or the apparent noon times, and the length of the day is shorter and longer based around when noon happens and how much daylight you have. So that gets to be confusing if you're trying to set your clock. So they did something in 1883. They standardized the time zones, and they made it where you now have something that is more averaged out. Because back in the day, before that time, if you were, say, located in San Antonio, you would look overhead, the local astronomer would do his thing, he would set his local time, and then you would set the clock tower in the town to a certain time, and you would toll out noon at that time, and it was based on that local astronomer or some smart guy or gal's measurement of the daytime, and he would pick when the sun was directly overhead, and you would set your clocks, or you would use a transit telescope, and you would set your local time. And if you were over just slightly east or west of there, let's say that you were over in Houston, then you would have a different time set in Houston than you would in San Antonio, because you would be located at a little bit different longitude line, and so noon would happen for you sooner in Houston than noon would happen in San Antonio, and so your clock would be off by that distance. That actually becomes useful later on when you're trying to tell your location and longitude. But it does cause a problem if you're trying to conduct business. So for the purposes of conducting business, they lumped everybody in a 1 hour zone into the same time zone, and that winds up to be about 15 degrees from one side to the other. And then the time in the middle of that is exactly on, and then plus or minus each of those time zones, you get 30 minutes one way, 30 minutes the other way, and you get your time zone. Now, that's useful for conducting business, but not if you're trying to set your telescope to tell it where to point at Mars, because you're going to be off by up to 7.5 degrees probably. And so what you may need to do is your program that's in your go-to telescope may need to correct the time for your longitude versus your time zone time. So it takes your time zone time, your longitude time, and corrects for that to know exactly what stars are going to be located overhead. That's a useful thing to know if you have a go-to telescope. All right, so we talked about the solar day being a little bit off and the calendar being a quarter day off. We had a big reform. Julius Caesar actually conducted a reform and corrected that to a better degree, but it was still a little bit off. And so the Christian church adopted Julius Caesar's catalog because it was the best thing, calendar. His calendar was the best thing going at the time. But by the year 1582, the days were off enough that it had built up to be 10 days off of the correct day for Easter. And so when you were looking at trying to find what day was Easter, they actually had like March 10th versus or 10th or 11th versus the 21st, and it was off. And Easter was supposed to happen on the spring equinox, and so it was noticeable by then. And they decided they needed to reform it. So Pope Gregory, around that time, reformed the calendar, and they had to actually drop 10 days or so off of the calendar to account for that difference, and then restart the calendar so that it lined up with what the stars were showing us. And we call that now the Gregorian calendar, and that's kind of what we've been going with since then. On an interesting side note, the Omar Khayyam had a 365.24, etc. onto many decimal places. He figured out the exact length of the day to a very precise degree, and he's the same guy that wrote the Rubaiyat of Omar Khayyam, Omar Goodness. And Omar Khayyam was a very interesting fella. Besides the fact that he was a good astronomer and a poet, he did a lot of really cool stuff. I would highly suggest looking up Omar Khayyam. But in the Western world, we credit Pope Gregory's reformation of the calendar for the way that we look at our year as 365 and a quarter days, and that's what we've gone with since then. We do have to include a leap year every now and then to reset us back to that quarter of a day, and y'all should all be familiar with the idea of a leap year. So that gets us through keeping time, how the stars and the sun are slightly different, and how that makes our length of a year different. Let's look really quick at the moon, and that'll be how we'll wrap up this chapter. Now, you'll notice up here I have the moon, and this is a very special moon model. It was based on Lunar Reconnaissance Orbiter data, and so the craters that this shows are to depth relief correct. They're to scale. And it has a very nice little LED sun projector on it, and I'll just turn this on and give you the moon. And so as this is moving, you can see the phases. It's going to wrap around and find today's actual moon phase. So right now it would be full. It's been working its way up to full, and now it's going to work its way gibbous all the way around to new. And so this is the last quarter moon. And then pardon the bright lights that'll show up here in a second. I'll get rid of them as soon as I can. But now the sun is going to be a lot closer to the moon, and so the sunlight, you'll see the moon at morning and in the evening. It'll start to come up here in a little bit after the new moon. So now we have a beginning crescent moon. I'll try and block that out a little bit. We're a couple of days past a new moon, and you can see it looks like a couple of 3 days into the cycle. Now, if I can kick this on the manual and step it a little bit, I'll try and do there. So if you look at the moon now, it's lit up about half. Half of the moon is lit up. But we don't call this a half moon. We call this a quarter moon. And this can be confusing to people that have never seen it before. But a quarter moon is lit up halfway. And the reason why it's called a quarter moon is the moon is a quarter of the way around its cycle around the Earth, because the moon's going around the Earth. And so if the sun's on one side, the moon is a quarter of the way around. Now when the moon gets around here to full, it's directly opposite the Earth from the sun. And then when it's over here in the third quarter, it's going to be the third quarter away around, and then it'll come back around to new. And then it'll be first quarter full, third quarter new, etc. And as it's working its way around, the moon phase goes from crescent to quarter moon to then gibbous, and gibbous is the moon as it starts to fill out the circle, and then it goes to full, and that's waxing gibbous. Waxing means it's on the way towards full. And then after full, it'll still be gibbous, but it'll be declining, and then we call that waning. So that's waning gibbous until it gets around to third quarter. And then from third quarter, it goes back to crescent, and then gets all the way back around to new moon. Now, interesting thing about the timing. A new moon will happen always right at sunset, because from our perspective on Earth, the moon is lined up with the sun. And so if the sun is setting, the new moon is also setting with it. And then a day later, the sun will set, and then the moon will set a little bit after that. A couple of days after that, the sun will set, and the moon's still visible, and it's crescent, and then it'll set. And then 7 days later, the moon is a quarter of the way around, the sun will set, and you will see the moon directly overhead. It'll be a quarter phase, and it'll be half lit up, and that'll be 7 days into its cycle. Then as it goes gibbous, it goes waxing gibbous until it gets to full, and then the sun will set and the moon will rise at sunset. So the sun goes down, the moon comes up, and it's directly opposite the sun, and so you get a full moon. Then it'll continue on its pathway. The sun will set, it'll be dark for a little while, then the moon will come up, and then it'll go through the sky as it's waning gibbous. And then later on at three quarters, the sun will already be down for a long time, and it takes a while, and then the moon will rise, and it'll only be up for a quarter of the time, and then the sun will come up behind it and wash it out. Those are the mornings when you get up in the morning and it's kind of odd. You look up and you say, why am I seeing the moon at 10 o'clock in the morning? And it's kind of odd. But that's the cycle of the moon as it goes through its phases. The moon as it goes around also causes tides. So let's talk about that for a second. If the moon is lined up with the sun, let's say I'm the sun and this is the moon. If the moon is lined up with the sun, this would be a full moon phase, because the moon is on the other side of the earth from here. So the moon is going to be tugging its maximum against the direction of pull, and the tides will be very strong. Now, as the earth goes around and it's lined up where the moon is a quarter of the way around, then you have the moon pulling this way and the sun pulling this way. The moon has a little bit stronger pull, but the sun also gets a little bit pull. And so you actually get a little bit of that canceling out, and you have lower tides. And then when you have a new moon, the sun and the moon are on the same side, pulling in the same direction, and you're going to have your highest tide. And so your highest two times that you have tides are at new moon and full moon, when you get the direct pull opposite of each other of the sun and moon, or they're pulling together in one direction. Then when your moon is here or here, then you're going to have them offset from each other, and you're not going to have as big a tides. So if you're a fisherman and you're watching your cycle of tides, you have the neap tides and the spring tides. And I believe the neap tides are the lesser tides, and then your spring tides are the ones that come up a little bit higher onto the banks. And so when you have a new moon and a full moon, you're going to have bigger tide differences of height. And then at a quarter moon and three-quarter moon, you're going to have less difference in height between low and high tide. Then last subject for this time is eclipses. So again, with our little handy stick being the moon, my face is the sun or whatever, and then this is the earth, obviously. So if you have an eclipse of the sun, the moon is in the way. You should be familiar with that. Well, think about this though. The shadow that this smaller moon versus a bigger sun, the shadow that it's able to block out the sun, but only for a small region, because it's kind of far away and it's small, and so it's casting a small shadow in a band across the earth. And so every time that you have a solar eclipse and the moon is in the way of the sun, that's a solar eclipse, you're going to have a stripe across the earth of where that eclipse is going to be totally blocked out. And then if you're not exactly on that stripe of totality, then the moon is going to be a little bit offset from the sun from your point of view, and it won't completely block it out. So if it was blocked out here, but you were slightly offset from my eyeball, then you could see that you wouldn't see a completely total eclipse. You'd only see the total eclipse if you were directly in line with my eyeball. And so that's one point of view from a solar eclipse. From a lunar eclipse point of view, again, my head being the sun, this being the earth, and this being the moon. So if the earth is directly in line with the moon, you're going to have a bigger shadow zone over here, and everyone that's on this side of the earth is going to see the moon in that shadow, the umbra. If it's a little bit off into the gray zone before and after, that's the penumbra, and then you get the umbra. So then you get a total lunar eclipse. And the reason that doesn't happen all the time is that even though the moon may be on the other side of the earth, you still may have an ability for the sun to line up and illuminate the moon, even though it seems like every time that the moon goes on this side and you have a full moon, you should also have an eclipse. But you don't, because the moon may be aligned slightly higher or lower, good enough for the sun's rays to pass by and hit it, and you're only going to get a lunar eclipse when it passes through the direct shadow. And so that's why you don't get a lunar eclipse every time. It's because the Earth's orbit versus the sun is at a little bit of an angle, and so then the moon's orbit around the Earth is a little bit of an angle, and so those two things have to counterbalance perfectly and line up for the Earth to be in line with the moon to get a lunar eclipse. So that's the difference between a lunar and a solar eclipse. A solar eclipse is only going to be totally dark in one little stripe, whereas a lunar eclipse is going to be totally dark for everyone on that half of the planet, pretty much. So one other thing, in the year 2017, there was a total eclipse that happened in the United States. It went from Oregon all the way down to Florida, or the Carolinas basically, and it went right across the United States, and the path of totality was visible throughout the entire United States. So OC Astronomy actually made an expedition up to York, Nebraska, and I'll put a link in the description and maybe a link right here too if I can manage it, and link to our video of OC's expedition to the zone of totality, and you can see a video of what it looks like to have a total eclipse. It was very exciting. We were out on the lawn, and thank you to the people of York, Nebraska, the college that's up there, for letting us sit outside their library. We had a really good time. So that's how the eclipses happen. That's about all I can tell you about that. I'm trying to think of anything else. I've told you about how the earth appears to move, how the sky appears to move, how the seasons appear to happen because of the tilt of the earth, how to keep time and the difference between a solar day and a sidereal day, how the calendar needed reform and eventually got reformed, the phases of the moon and the tides, and the eclipses. And that should be chapter 4. I hope you had a good time. I hope it made this brief enough to where I didn't go on and on. Please give me a thumbs up and like the video if you enjoyed it and if you got something out of it. And this is Dave with OC Astronomy. Clear skies.